Okay, so welcome back to CyberPhysical Systems. So today we're going to start chapter 1, and the goal is to go through half of chapter 1. So in chapter 1, we're going to look at these topics. First, since chapter 1 is about the introduction to systems in a very general way, but trying to make a link to the mathematical foundation that you already had. So we're going to look at the study of systems, and then how we express and what the importance is of being able to express system requirements for different domains, because one thing that we're going to keep coming back to is that these complex systems will tend to be, even though they are heterogeneous, they're serving important purposes in specific domains. And what that means, and what we're going to be saying, is that we're going to need domain experts. So we'll come back to that. Then we have a few sections about describing systems. So standard forms and mathematical forms. The idea there is to link the system expressions that you are already familiar with, like if you're seeing things in signals and systems and control systems, those types of expressions, and trying to have those, not equations so necessarily, but the mathematical ideas stay with us in this course as we look at models and block diagrams later on, because the systems, those are the real tools that we're going to have. The complexity of these systems require that we model, and as part of those model and as part of those abstractions that we use block diagrams. Not easy to put it in equation format, but the ideas of input and output relationships, transfer function, controllability, observability, and being able to identify systems, as well as the concepts of steady state errors, those are important, and those are still going to be very relevant. So we're going to try to get today through half of these topics, okay? So when we talk about getting more into the specifics of what cyber-physical systems are, when we talk about cyber-physical systems, we are talking about a tight integration between computation, and later we're going to say embedded computing systems, and the physical system. And that doesn't mean that it has to touch anything or be connected to anything. I cannot think of a more pervasive and linked cyber-physical system than your cell phone. If you think about all the technology there, it's really linked to, from a physical perspective, to you. And you are linked to the world. So that is a cyber-physical system, your cell phone. These cyber-physical systems, they have, in many instances, stringent real-time constraints and requirements and safety requirements. So safety may be a bit more obvious. So if the system is complex, it's not a stretch to think that there is a lot of at stake that the system is involved with, but also this system may have to respond in real time. What that means is that there is a predetermined response time that if the system doesn't respond within that time, we can say that the system is not performing or the system is failing because something bad is going to happen. Okay? Different than, whether your web page loads in half a second or 1.5 seconds. That's different. That's not an astringent. That's not an astringent real-time requirement. So a web server doesn't have that. But an airplane guidance system does have that. Okay? It has to respond. So we're going to be talking about those issues. And that requirement of responding comes from the fact that it's tightly coupled. The system may be tightly coupled with the physical system, with the physical environment, which may be deterministic, may be random in nature, or stochastic, or even maybe beyond that, it may be a chaotic system. Okay? So the system may need to respond to that. So in this chapter, we'll give you a general introduction to system with regards to the specifications and the features and requirements of cyber-physical systems as we get into the course. Now, I talked about the multi-domain nature of cyber-physical systems. And what does that mean? And you can see how there being an emergence of certain study programs or degrees that are designed to bridge the gap between the classic modalities of knowledge, let's say of engineering, like mechanical, electrical, computer, and domain specific, because as systems have become more complex, you need that someone with the knowledge to bridge the gap into the domain expertise. So one clear example, biomedical engineering. If you are designing or are part of a design team of a life support system that has all kinds of sensors, well, the domain experts are the physicians, and you have your expertise in, let's say, computer or electrical engineering, and there is somebody else that has expertise in mechanical engineering. You are the ones that are going to start to really put together this complex system, but it's to serve that specific domain. That's what we mean by domain specific. And the complexity of the system and the nature of the problem, life support, you're trying to sense and react and deliver drugs and support and notifications, given that physical system, the person, the patient, the gap is so large that you need someone just to kind of think of it as translate. Okay? So that's a good example of the multi-domain nature of cyber-physical system, where you have your classic mechanical, electrical, computer, software, system, then you have the domain expert. So taking care of requirements with that view of the domain expertise required is important. So this chapter, from a system perspective, classic kind of mathematical system perspective, provides a good introduction, but not just an introduction, a strategic introduction to what we're going to be talking in the next couple of chapters. The next chapter, embedded systems, and then cyber-physical systems specifically in chapter 3. So predicated on the sort of overall broader systems in this chapter. So what do we mean by a system? So it's simply, and if you have taken the course of systems engineering, you may remember this, is a combination of elements that together perform a function not possible with any of the individual parts. So that's pretty close to the formal definition that we had in systems engineering, okay? But it can also be a process. A system can be a process. In that course, we talked about open versus closed systems. Many processes tend to be more open than non-process systems. So we can look at it as a process as well. And broadly, if we define a signal as an entity, a broad entity, and I know that we immediately think of a voltage, but that's not what we mean here. When we talk about a signal, it's an abstract entity that is coming in or out of the system. It could be inside of the system, and then we're going to call it something different that you maybe have heard. We're going to call it a state variable. But for now, if we're just looking at a system as a process that transforms an abstract entity, an input, into an abstract entity signal, which is an output. So we have a transformation. So this over here, sort of a genetic transform operator. So as I mentioned, a system also can be looked at and represented by a state vector, which I can identify if I know the initial state. If I know the initial state, and I know the input over some time interval, then I can predict. And if I know the nature of the system, that transfer function, that transfer operator, I can then predict what is going to happen to that input for any given time afterwards. If the system behaves that way, then I have a dynamic system. And most systems are. And depending on how many state variables that I have in the state vector, which can translate to the number of components, and to kind of remind you of your signals and systems, when we say components, I'm thinking integrators in those block diagrams that you're familiar with. And when we say state variables, we are talking about the output of the integrators. So all this terminology that we're going to be using, a big part of this chapter is trying to make that link from that very math-intensive course that you took to this one, where we're not going to use equations that much, but the mathematical concepts we do want to utilize, okay? Or the mathematical ideas. So, back to another way of saying the definition of system that we had in systems engineering, that a system can be an organization with a purpose. We talked about a system having a mission, and it has a structure. We talked about structural organization or physical organization, and we talked about functional architecture or functional organization. So the system has this purposeful structure and has these components that are interrelated and interdependent, meaning that for the system to achieve its function and perform its mission, all these components have to be there. They're all not the same level of importance, but you can always tell that some functionality will be detracted from the system if at least one component is not there. Otherwise, it's a superfluous component and it's a bad design. But I'm not saying that if you take away a component that the result would be catastrophic. They all don't have the same contribution to the mission of the system, and that's why we have tools to actually rank that. And if there is something that is really important, maybe we have to add, actually on purpose, we add redundancy, because we really need that part of the functionality. So these elements have all these different activities, what they do, attributes. They can have their own components. Things like delimitations, states, and again, they influence one another. That's that interdependence. It can be a direct influence or indirect. To be able to meet their functionality within the system and overall, and achieve the overall goal of it. So the main things that we want to keep in mind are activity. So that represents what the system is reacting to, basically what's going on with the system. What's the overarching activity that is going on in the system that determines its nature, its behavior, and therefore its states. Then we have attributes, which are the properties of entities of the system. Then we have the entities, which are objects of interest. So this is very important, of interest, depending on the level of abstraction over which we are performing the analysis, at the set of entities of interest may not be the same. So that's important to remember. And then we have the state. Again, the state is the collection of variables, or if I want to omit saying that, I can say the state vector, necessary to describe the system at any time relative to the analysis that is being done. So that's the objective of the study. With regards to the domain that is linked to the system, and everything else that is in it. And those are going to be different for different types of systems. So here I have two examples of two systems that are complex, but I can narrow the scope by narrowing the state variables or the analysis that is being done. So let's say that the type of system in the first example is a laser welding activity. So this is a laser welding station in a production line. The attribute of interest could be two of them: the welding speed, how fast I can weld a part, and that will give me the capacity of that attribute. So parts, how many parts per minute can I do? And then if I have to do 2 weld points per part, then so I can calculate that. Now I can have multiple welding machines, and the state variable for, let's say, this analysis that I'm thinking about can be the status of the welding machine. Is it welding or is it waiting on a part to be fed to it? And let's assume that once you fed this part, the machine has actuators that it can, if I need to weld multi-points, then I can do that. So let's just hold on to that, and let me describe the other one, banking. But let's say that the scope has to do with the tellers at the counter, so that, you know, we don't, so we kind of narrow that. Servicing the checking accounts or the accounts of clients, they're making deposits, and or transactions, let's call it. They're making a transaction. It could be a withdrawal, any type of transaction. Then you have the customers as an entity. And again, the state variables are the number of busy tellers and also the number of customers. Notice that in this case, we didn't identify the tellers as an entity. Or we didn't, in the previous one, we didn't identify the parts as an entity. Because it really depends how you want to state your problem and do your analysis. If I go back to the first example, maybe what I want to optimize is the number of machines that I need to have on that floor. So that is a deterministic problem. If I know, if I want to optimize for, make sure that all the machines are busy, and if I have a history of the orders coming in, then I may have some parts that are queued up and waiting. If I want to make sure that I get the parts out as fast as possible, I may optimize for the highest number of parts or orders that I get, or somewhere in the middle. And that's driven by perhaps some type of business decision system or decision process. But it's deterministic because once I say I'm going to service this many parts, if I know the speed and the nature of the welding and how many weld points and how many machines, then I can come up with how many machines I need. Very straightforwardly. But let's take a look at the other case, the banking. It's not easy to predict when you have in a process like the second example, sort of a customer service activity or process. It's not easy to say this is the maximum, this is the minimum. Well, the minimum is always 0, but what is the maximum? What is the average? So if you think about it, that is more of a stochastic problem. It's not deterministic. And we have tools for that. We can use queuing theory for that. And we can say, well, the probability of a customer arriving is this if it obeys some type of distribution. So, and these things usually do obey some type of distribution. And the service time, because it's hard to predict what type of transaction a customer is going to have. So I can at least get a sense of the distribution of the service time probabilistically. And using queuing theory, then I can actually optimize for the number of tellers that I have standing, and understanding that sometimes they will be idle, but I can actually optimize using queuing theory for the number of tellers. And one parameter that I could even add there is how much wait time I can have. I can assume that the customers are going to tolerate. Because the way that is expressed now, that's not a parameter. That's not a parameter. So the modeling of the queuing theory with this setup would be would not take that into account. So this is devised to kind of, with two simple examples, give you an idea that systems are going to have different ways of being analyzed, but they all are going to have this activity, attributes, entities, and state. So let's keep talking about systems and systems constraints. So again, it's a collection of interacting elements. There are many ways to say it, and I have, like, every time I wanted to basically express it in different ways. Collection of elements with cause and effect relationships. That's another way of. And then we have system response. System response depends on initial conditions, when that input comes, that input of interest. And another way of referring to state variables is energy stored in the system. And then you can also have external forces or external excitations beyond the input signal. So one way of doing system analysis is by modeling this system and model the response deriving or from other mathematical analysis techniques. But as you'll see, even though I'm going to show you the equations, just to remind you of those signals and systems course, for us, the bottom line is that it's going to be inadequate or not feasible. Okay? So the strict mathematical formulation is not going to work for us. We will still want to remember the concepts. There are inputs, there are outputs, there are feedback mechanisms. We have internal states that tend not to change. So we want systems that every system is changing, but at least over a long time or a time of interest, or compared to the rate of change of any input of interest, the system remains static. The system, the characteristics of the system is static, and that way you can say that it only reacts to the input and to the external excitations. And then, if you know the initial conditions and you know what's coming in, and you know the transfer function of the system, then you can predict its behavior. Because if the system is changing itself, that's another level of complexity. We're not going to be talking about that in the course. It's not that type of system. Okay? But that doesn't mean that the system cannot be reconfigured. Okay? So let's make sure we don't confuse that for a specific activity, the system is static, but it can be reconfigured and it can become a different system that has different characteristics than any that is not present in any of the components. Another characteristic of the system is that it has boundaries. So we can clearly define the boundaries, again, from the perspective of the analysis that we want to do, and that is also called a system observer perspective of the description of the system. And if we can do that, we can say that the system is observable. And it is important that we can observe the system. So system can also be a phenomenon. So we have, it can be an actual hardware system, it could be a process, it could be a service, it could be a phenomenon, a natural phenomenon. So in the broadest sense. It also may be part of a larger system. So we have systems of systems. So how far do we dissect or break down a system? Well, as far as it meets that definition. The definition of the main concept of the definition. Does it have a mission? Is it a collection of different components working together that are interdependent? And is the system doing something that is uniquely done by that collection of all the components that cannot be done by a single component, or if you take a component away? And if you have a system and you break it down into subsystems and it meets the definition, then you look at the next layer in the hierarchy And as long as you have that, those conditions are met, you have subsystems until you get to a leaf component. So, so let's go back to the concept of state and a state variable. So it's really, the concept comes from a mathematical description and a state variable representation of system classically seen in control systems. And just like we mentioned before, if we have a mathematical description with a minimum set of states, let's say n number of states, and I can say that together with the knowledge of those variables and an initial condition and knowledge of the input after some arbitrary reference time t0, that is sufficient to predict the future behavior of the system output and the system state for all time after t0. And that is the dynamic behavior or state behavior of the system, in the sense that it's characterized by that response. That is the transfer function of the system that we'll see we can express as an input-output strictly, or if we want more visibility inside of what's going on in the system, the states, then we can have the response expressed as a state variable expression. And the number of states, the number of minimum states required to go through this exercise effectively is what we call the order of the system. Even with system models, which is more of what we're going to be talking about here in the course, you can have a state-determined system model. But again, you still have states, and these states, the relationships in them or between them, because remember that the states are the output of these components and they are interrelated, they depend more on rules, heuristics, and also equations. But a model is more than just a set of equations. And classically, the state has been related to the energy in the system, and present as part of the description of the system is the time derivative of these state variables. So if you remember back to your integrator type diagrams in systems and signals, or signals and systems, the is the output of the integrator, the input is the derivative of that, right? So that was always present because you had this type of element. And again, the value of the state variables, the knowledge of the input, and the initial conditions provides enough information to derive the response of the system, and the values of the state variables describe the transfer function of the system. So you probably remember this example. So I want this simple mathematical ideas to stay with us so we can carry them forward, and they hopefully become second nature as we think about complex systems, because they're still useful. So you're probably seeing the example of the spring mass damper system and how it is equivalent to an RLC circuit where we have the state being charged. I'm just going to pick the RCL network where the state is charged. So we have the time derivative of the charge, that's the current. Then we have system parameters, the inductance, the resistance, the capacitance. And in this case, we have the input function being a voltage to that network. And you can take, if this is a series RCL network and your input function is a step function and your output of interest is the oscillation, let's say, across the resistor, okay? Your voltage across the resistor, then you're going to see that oscillatory decaying oscillator output as a result of that input. The same way that with the mass spring, you would see that if you give that system an impulse, a bump, it will start oscillating, but eventually it will die out and stay at some point. So I could have taken another type of state variable. Didn't have to be the charge, but this is what is easiest in this case, most natural, if you will. And the important thing is that we pick the right state variable to serve the purpose of the analysis that we're trying to do. So you can have, there is no unique set, you can have different sets of variables, and as long as you can describe the system, that's the important thing. So this type of block diagram you're familiar with, and as we progress to more elaborate type of block diagrams that tell us about behavior instead of a mathematical operation, this is where the link is and how you can think everything started, if you will. So even with these diagrams, if you remember, why were they useful? Why were they useful as a tool? Why were they effective? It gave you a visual transition from, although these were simple systems that we could describe with equation, it gave you a visual, tangible transition to something to something that you could put together, that you could execute, that you could bring to life. Because you could say, well, each box now is going to be an op-amp. And if I want to make a circuit of that, I can. Because each box is going to be an op-amp type circuit. Either an amplifier, an integrator, a summer. But I can make this with op-amps. So hopefully you can appreciate that block diagrams help you make that transition from words. In our case, they're going to be specifications and words, but in your previous courses, from equations to something that you can actually build. And that's what we want to get to, something that we can actually build, but build correctly, according to the equation or according to the specification in our case. So these blocks could be linear or nonlinear. The way of visualizing the flow through them is also called block diagram algebra. And if it's a scalar signal, then there are, very simple equations, but they could be multiscalar signals in which these blocks are really matrices. So that's the next step from this type of diagram, the next step of evolution. They can be matrices. But still you have algebra involved, block algebra, linear algebra, etc. So, as I mentioned, in this type of systems, your state variables are the output of the integrators, and in there, and the derivative is the input of the integrator. And in there, I recount, in case you forgot the steps to come up with this diagram. If you have the equation in Laplace form, that's how you basically go from the equation to the diagram. You know how many integrators you have by the highest exponent of the Laplace transform, and basically you draw those, and then you have the state variable, which is the output, and the derivative, which is the input, and then you can draw a summing junction at the beginning, and then each of the outputs of the integrator or your state variables are basically a scale as they feed back into that summing junction, if you remember that. We're not going to be doing that stuff here, okay? I don't want you to think that it's the same. What I want to relate to you is that the concept of states, even for complex systems, output, input, and being able to have a block diagram where you clearly understand the state and the output input relationships along with the state trajectory, giving an input, that part is valid. That's the mathematical idea. That's the mathematical idea, okay? So transfer function, remember the Laplace transform. So if we have your linear time invariant system, and we have the state variable expression, which has two parts, the state equation, in which the derivative vector is equal to some matrix times the state plus some other matrix B times the input, then the output is some variable times the state plus another variable d times the input u. So in this case, we have the state x, we have the derivative of the state, we have matrices, and then we have an output equation. Now, this type of differential equation or Laplace transform, which is really a differential operator, two set of equation of a state variable representation of a system, if you remember something totally different that maybe you are not linking with signals and systems, if you remember your 312, a state machine has also the same two equations. You had in a general state machine, which is more relevant to the stuff that we're going to be talking about, because a lot of software can be implemented as a state machine and hardware as well, and they can be complex. But if you remember, you had a state, the output of the state register. That's your state. You had a next state. Well, that's the derivative of the state if you're trying to equate the next state, the input to the flip-flop. The state is the output of the flip-flop. The input is the derivative of the state, the input of the flip-flop. The flip-flop is your integrator. And then you had a logic block that took the input and the state and made the next state, the derivative. Well, those logic blocks are matrices A and B. And then you had the output, which was, the output Y was a function of the state and the input. So that's the output logic, if you remember. Okay? So there is congruence. In all these disciplines, there is the same, so the same way that we see that paradigm in controls, linear systems, and in logic design, we're going to see it, and we need to use it. It's been proven to work. We want to use it in complex systems as well. So, sure, if you can solve the equation and you get matrices, and that's all good for completeness, but we want to keep going. And remember that we can have the input-output expression or the state variable. So the state variable is when you see all these components, like the previous diagram. You can also look at things as a single box, input, output, and that's what I care about. And the transfer function is just this rational polynomial in the domain that you are working. S, in this case, we're talking about the Laplace transform. All right, so now let's go back to our system discussion and talk about system specifications and the technical requirements that they represent. So they need to be represented, system specifications, because it defines a baseline and include these parts. These are the most important parts. In the system engineering course, we go into a lot of other parts, but this is And in that course, I say that, it's kind of broad, but we are trying to really come up with these complex computing systems. In reality, that's what they are. But think about it, we need user requirements. They are important. The user pays the bills. So in my mind, they're first. User requirements, and then in my mind, the next thing is feasibility is the next thing. Okay? Is it feasible? And once I keep going down the line, if it's feasible, then okay, I can go into operational requirements. So that's the main thing that it needs to do. And then to me, in complex systems, maintenance concept, we talk about that in the systems course, systems engineering course, maintenance concept, the sustainability of a design is so important. There are other attributes, there are other things that we need to worry about. But for now, let's just concentrate on this. Believe me, they are enough. And those operational requirements drive a top-down functional analysis. Top-down because it really comes from the user requirements. It drives those top-level functional analysis to identify some metrics. Metrics, critical technical performance measures, and this is terminology from systems engineering, that's why I'm using it, and design-dependent parameters. These metrics have a specific meaning in the context of systems engineering. Critical technical performance parameters are parameters that are non-negotiable that you have to achieve, and there are ways to weight and measure the relative importance of all parameters so you can distill which ones are the critical technical performance measures. And there are tools for that, such as the house of quality that we use in systems engineering. And then we also have design-dependent parameters, which tend to be others that are non-critical, but they are important as well. And we should take into consideration. So that system specification is a baseline. It's actually a minimum set of documentation that you should have for any system that has a decent amount of complexity and that you want to execute and bring to life, and you want to engineer with a good shot of success. You have to have a good system specification. And you have to keep doing this for the subsystems as well. You have to basically provide enough information so that research, design and development can be done to bring the system to life. And research, for example, in the case of a feasibility study, research is done. The more versed you are in technology, the more you can get close to saying, yes, we can do this. But it is not until you start really peeling the onion and getting in there that, unless you have done the same thing before, okay, and you're just repeating something that you have exactly done, you may not know all the details until you start getting in there and trying to put that system together. And that started with that system specification, so you don't overlook anything as early as possible. As early as possible. So you may have also subsystem specs. And these subsystems could be assemblies, sub-assemblies. A subsystem could be a computer program. So a computer program could be part of the system as a component, but a piece of software could be a subsystem. That may be two different things. Depends on what it does, if it meets that definition that we talked about. Equipment also can be subsystems and facilities and so on. Again, anything that is, and that's why it's so important to start putting together these diagrams and block diagrams, because then you can start seeing the interactions. And if you are comfortable with the definitions that we are sharing, then you are able to discern, okay, this is the system, this is the boundary of the system, this is a subsystem, this is a component, and you can start putting good specifications together at this point. So again, part of subsystem specs can include effectiveness and also the system performance. All that is part of, because each subsystem is a system in itself. And support characteristics, which are derived from the system level maintenance concept that is at that level. I want you to be aware that a way to deal with complexity is what is called order model reduction, or reduction of the order of the model. Another way to think about an order of the model is the complexity. So the higher the order, the more complex the model is. And remember, the order is the number of state variables that, even though you are not expressing that as a differential equation or a Laplace Transform type algebraic expression, you still have state variables in a system. So a way to deal with complexity may be to reduce the order. And I want you to at least be familiar by name and have a reference of methods that have been used to reduce the order of models. And for now, I'm just going to just show here a few of them so you know that exists. There are formal methods of reducing and this is not a comprehensive list, okay? In big data, we have some other things. For example, we can use principal axis decomposition, and there are many techniques to reduce the complexity and try to figure out what's important and what's not so important, so I can reduce the complexity to make my analysis more feasible. So I want you to at least know these methodologies and know that they exist. So I'm not going to read them to you, but they're there, and you'll be getting these slides, so it's a place to start. Now I want to remind you of a lot of what we have talked about, but now getting closer to our types of systems. So I want to start talking about discrete time systems, because a lot of this, well, most of the functionality and behavior that we are talking about can be discretized. If we can sample appropriately, we can discretize a system. And there is enough technology available that we can discretize almost anything. Okay? So, just reminding you about your knowledge of discrete time signals, which are discrete in time at the sample time, and they're basically a sequence of numbers, right? So you have your signal and you look at it and you write the value, like if you were, you store the value as a number in digitally, but it's really a number. It's not a abstract physical quantity anymore. It's a number. That, in essence, is what we mean by sampling or discretizing a signal. And we can have a discrete time system that processes that signal. So now, since we have numbers, the discrete time system is basically a program or some type of digital hardware. And it produces a discrete or a collection of numbers out of that algorithm or computing engine. And that's the output. That sequence is the outputs. And yes, if we need to, we can actually convert that to some type of abstract quantity or physical quantity. We can make that happen we have devices for that. So, discrete time science system is really how all signal processing, complex or simple, discrete time processing is how all signal processing, or vastly the majority of signal processing, is done. So we have the same type of equations. The only thing that we don't have differential equations, because now we have discrete samples in time. So what we have is what we call difference equations. So instead of, which is more like the example that I was talking about of the digital system, where the state is the output of the flip-flop and the derivative is the input to the flip-flop. So in a sense, that is a delayed version of it, okay? Because the quantities can be delayed by a sample cycle. The quantities can be delayed by a sample cycle, and that's equivalent to that integration step. So that delay is equivalent to an integration. So that's why I say that a flip-flop digitally, or a register, which is a collection of them, is equivalent to a digital integrator, if you will. So we can have discrete equations. We can sum two signals. We can scale a signal. So these are still linear systems that are homogeneous, and we can scale. So here we have, well, I'm going to stop here, because I think it's time, and we'll pick it up on Tuesday.